Learn efficient pharmacology, passage of drugs across the plasma membrane, part 4, membrane transporters. In simple diffusion, molecules move passively from a region of higher to a lower concentration across a semi-permeable membrane. Now there are two questions. First, what happens to molecules that cannot cross by simple diffusion? For example, ions or large polar molecules. Secondly, can a molecule cross the membrane against its concentration gradient? Let's take a beaker filled with water and separate the two halves with a membrane. Now, let's add a highly ionizable drug A to the left half. Since drug A is ionized, even with a concentration gradient, it wouldn't be able to cross the membrane by simple diffusion. To solve this problem, let's insert a transmembrane passage for drug A. Now, when this passage is open, drug A can freely move to the right by diffusion. No energy is required because drug A already has a concentration gradient and the passage merely facilitates the diffusion. So this process can be called facilitated diffusion. Since no additional energy is required, this, like simple diffusion, is also classified as passive transport. What shall we call this passage? We call it based on what it does. Since it transports solutes like drug A by carrying it across the membrane, it can be called a solute carrier transporter or SLC transporter. Clearly, the SLC must have a transmembrane domain. So in this example, the SLC mediated facilitated diffusion. SLCs are a major family of membrane transporters. In a cell, SLCs mostly mediate the entry or uptake of solutes. So are transporters and channels the same? Not exactly. One fundamental difference is that in channels, the channel is not opened by the solute per se, but as a response to a stimulus which is usually electrical, mechanical, or chemical. Once the channel opens, the solute merely flows through it along its electrochemical gradient. But a transporter is not so. It is the binding of the solute that causes a conformational change in the transporter. It is this conformational change that facilitates the transport of the solute. So from now on, this is how we will represent a transporter. We will discuss ion channels in detail in a later video. Now in place of drug A, let's add a highly lipid-soluble drug S to the left half of the beaker. Since the drug is highly lipid-soluble, few molecules might immediately cross the membrane by simple diffusion. Now, why don't these molecules move back to the left, even though the drug is lipid-soluble? The problem here is not lipid solubility, but the fact that these molecules must move against their concentration gradient. Logically, what is required is a transporter that can carry these molecules against their concentration gradient. This will require energy. So, in addition to a transmembrane domain, this transporter must have a site to bind the energy currency of the cell, ATP. That is an ATP binding domain or cassette or ABC. ATP we know is a nucleotide. So the domain that binds ATP is also known as the nucleotide binding domain or NBD. Due to the presence of ATP binding cassette or ABC, this transporter is called the ABC transporter. Since it utilizes energy in the form of ATP, this is an example for active transport. This is a very simplified schematic representation of how an ABC transporter works. In a cell, ABC transporters mostly mediate the exit or efflux of solutes. This table summarizes the characteristics of the two major families of drug transporters we discussed. This is an overview of the nomenclature of SLCs and ABCs. Here you can see a few more differences between transporters and ion channels. We saw an SLC mediating cellular uptake along the concentration gradient of the solute. We also learned that ABCs mostly mediate efflux against the concentration gradient. Now, the question is, can SLCs transport in the absence of a favorable concentration gradient? We will see that in the next video.